Hi, my name is Kenji Caponelli, and I will be leading this video titled Introduction to cQASM. We will start off with a brief introduction to cQASM, followed by an explanation of how to use it and most of the functionalities available with this software. cQASM was first released in 2018 as a collaboration between researchers at QTech and Intel Labs. cQASM is a quantum assembly language which essentially acts as a compiler of quantum circuits to specify the instructions for a real quantum computer. The aim of the authors was to abstract away qubit technology details and guarantee the interoperability between all the quantum compilation and simulation tools supporting this standard. It was developed in a way to be as general as possible and to allow for efficient programming of quantum circuits regardless of the hardware backend. Note that Quantum Inspire currently uses cQASM version 1.0. Furthermore, the slides in this video were created using the information provided on the knowledge base on the Quantum Inspire website. Now we will cover a basic example of how to use cQASM to generate a quantum circuit. Those already familiar with quantum circuits would likely find the implementation of cQASM straightforward. Here's an example of what a code block in cQASM might look like. At the bottom, we have included the corresponding circuit generated by this code. We will now go through each step one by one. First, all circuits start with specifying the size of the qubit register, as done here in command line 4. Secondly, we must initialize our qubits, specified here in line 7 by the prep_z function. Here we use range comprehension to specify the first two qubits. However, we will cover this in more detail in a few slides. Next, we specify the quantum gates that compose our circuit. In lines 10 and 11, we can see examples of a Hadamard and a C0 gate. We specify the qubits that they act on in the square brackets. Then, we finalize the circuit with a measurement. In line 14, we use the measureAll function to specify that all qubits must be measured. After a measurement, a binary register will be created that contains the outcome of the measurement. In this circuit, we use the measureAll function to measure all of the qubits in the Z basis. However, we can also measure and initialize in a different basis by using the prep_x, prep_y, and measureX and measureY functions. In this example, we could call the B0 or B1 variables to retrieve the binary outcome of the measurement on the first and second qubits respectively. We will see an example of how to utilize the binary register in a later slide. Finally, we can also decompose our circuit into subcircuits. A subcircuit is a way of structuring your quantum circuit. To create a subcircuit, simply begin a line with a dot followed by the name of the subcircuit. The following commands will then form a part of this subcircuit until a new subcircuit is specified. Please note, however, that subcircuits cannot be any of the reserved keywords used for commands and may not begin with a B or a Q, since these are reserved to denote the binary and qubit registers. Furthermore, they cannot contain a dash or non-basic Latin characters. Next, we will cover how to perform single qubit gates on multiple qubits. For every initialization, gate, or measurement command, we specify the qubit numbers that these are performed on. The input can consist of a list of numbers, a range, or a list of ranges. Here we show these three different cases performed with X, Y, and Z gates respectively, and the corresponding circuit on the right. For example, in line 6, we specify an X gate acting on qubits 0, 2, and 3. In line 7, we specify a Y gate acting on qubits 1 to 4, and finally, in line 8, we specify a Z gate acting on qubits 0 to 3 and qubits 5 to 7. We can also perform parallel operations in cQASM. This is performed by putting the gates between curly brackets separated by the pipe symbol, as demonstrated here in command line 7. Please note, however, that not all backends are capable of parallel operation, and therefore might instead compile the circuit in a way that executes the gates sequentially. Furthermore, it would not make sense to request parallel operations of gates on the same qubit. Another nice feature of cQASM is the ability to create qubit aliases using the map function. This is done as shown in command lines 5, 6, and 7. We start the command with the map function, followed by the specified qubit or binary register and the keyword that we choose as its alias. In this example, we first prepare both qubits, then perform a Hadamard gate followed by a measurement on the first qubit. Then, using the binary register B0, we perform an X gate on the second qubit conditioned on the measurement outcome of the first qubit. This is represented in the circuit on the right with the 0 symbol above the X gate for the second qubit. Thus, when programming the circuit, we can specify the alias to enact a gate instead of the qubit number. This can be quite convenient in the construction of certain quantum circuits. We can also implement static loops in cQASM. This enables us to repeat a specific subcircuit, which is often an essential part of certain quantum algorithms. As an example, we present here Grover's algorithm. To implement a static loop, we simply append an integer between brackets immediately after a subcircuit name. Here, we perform this by adding a 2 in brackets right after the subcircuit Grover in line 10. Note that if we were to add a measurement at the end of the Grover subcircuit, we would be measuring the qubits twice. To avoid doing this, we should create a new subcircuit and then add a measurement here, as shown here in lines 25 and 26. Here we provide a list of gates that can be implemented on cQASM. We have the usual Pauli gates and the Hadamard gate, then arbitrary rotations about the x, y, or z axis, and also positive and negative pi/2 rotations about the x and y axes. Furthermore, we can also implement S and T gates, then the important 2-qubit gates such as the C0, CZ, swap, controlled phase shifts, and also the 3-qubit Toffoli gate. Finally, we can also implement binary-controlled single-qubit gates, which can be associated with the binary register corresponding to the measurement outcome of one or more qubits. In conclusion, in this episode, we covered a basic introduction to cQASM, following some simple examples. We covered how to generate subcircuits, how to implement single-qubit gates on multiple qubits at a time, how to implement parallel operation of gates, how to use qubit aliases, and how to create static loops. In the next 2 videos, we will be covering more concrete examples of how to use cQASM for coding arbitrary quantum circuits.